guys, Ms. Gosling here. In this video, you're going to learn about Hubble's law. By the end of the video, you will be able to estimate the age of various bodies in the universe and the universe itself using Hubble's law. So let's go ahead and get started. So from this video, by the end of this video, you should be able to do the following things. You should be able to understand Hubble's law, the accelerating universe in redshift, and the cosmic scale factor. You should also be able to describe the cosmological origin of redshift. Additionally, you should be able to solve problems involving ZR and Hubble's law, and you should be able to estimate the age of the universe, which is super fun. So let's go ahead and dig into all of this. Let's start with the description of Hubble's law. So Hubble's law is a description of the speed at which every point in the universe is moving away from one another. But what's tricky about it is that it changes constantly because the universe's expansion is accelerating. So Hubble's law states that the speed at which an object is moving away from us is equal to Hubble's parameter times the distance from Earth to that object. Now, one thing that's really cool about this, or one thing we can learn from Hubble's parameter, is that the farther an object is from Earth, the faster that object is moving away. So the farther the distance, the faster the speed. So what I'd like to do is take a moment to talk about how we can use Hubble's parameter to determine the age of the universe. Now, before I do that, I do just want to remind you all, again, Hubble's parameter is not constant. It changes over time because the universe is accelerating. So when we were talking about using Hubble's parameter to figure out the age of the universe, we were talking about using the current Hubble parameter to figure out the age of the universe. So we know velocity is equal to distance over time. So that means that time is equal to distance divided by velocity. Hubble's law states that velocity is equal to Hubble's parameter times distance. So that means that 1 over h is equal to d over v. Therefore, 1 over h is equal to the age of the universe. Easy peasy. You do need to know how you can use this relationship between time, velocity, and distance, and velocity, distance, and the Hubble parameter to figure out the age of the universe. So given the Hubble constant, you need to be able to figure out how old the universe is at the time when that constant is measured. So now what I'd like to do is talk about cosmological redshift. Now, I'm going to just let y'all know right now, the next slide we are going to talk about where this redshift comes from. For now, I just want to talk about how we describe that redshift and use it to understand our universe. So we use the factor z to define redshift, to describe redshift. This redshift factor z is going to equal the velocity of the light source, v, divided by the speed of light in a vacuum, 3 times 10 to the 8th meters per second squared. That redshift is equal to the difference between the observed and emitted wavelength of light, and the ratio between that and the emitted wavelength of light. I know that this is a lot of new information. We will do some example problems with this so you can see how this equation might be used in the future. Before we do that, though, I do want to, as promised, discuss where redshift comes from. So when we talk about cosmological redshift, we are talking about the redshift of light emitted by distant galaxies because of the expansion of the universe. So when we are talking about a cosmological redshift, that is about the expansion of space-time. So all objects are going to experience cosmological redshifts. I want to differentiate this from Doppler redshift. So when we talk about the Doppler effect, what we are talking about is a change in perceived frequency because of the relative motion of two objects. So that object, the light or the sound typically that we talk about the Doppler effect, but also the light, the frequency of that light itself is not changing. It is just our perception of the frequency and wavelength of the light or sound that is changing. When we talk about cosmological redshift, the frequency and wavelength of the emitted light is changed because the light itself is expanded as it moves through space that is expanding. So that is the fundamental difference between cosmological and Doppler redshift. While the effects may be similar, their causes are deeply different. So now let's take the time to actually do the experiment, to do an example problem. A particular emission line in a distant galaxy shows a redshift z of 0.084. The Hubble constant is given below, and we need to figure out the distance to the galaxy. So d equals question mark. So to do this question, I'm going to go ahead and start with my equation that has distance. So our Hubble parameter says that velocity is equal to Hubble's parameter times distance. We also, so here I know h, I'm trying to find d, but I don't know what v is. However, I have the hint that I was given this redshift equation. So let's see if that's helpful. So we learned that z was equal to v over c, which is equal to delta lambda over lambda naught. Now, just looking at this, I can tell I don't know anything about any wavelength. That's going to be useless to me. But z equals v over c is quite useful because I know what z is, and c is the speed of light in a vacuum. That's constant. So I can write v as being equal to z times c, and I can now substitute that back in to my Hubble equation, my Hubble's law equation. So I can say then z times c is equal to h times d. Thus d equals zc divided by h, or 0.084 times 3 times 10 to the 5th divided by 68. Now, you guys may be wondering, hey, we've been using the speed of light as 3 times 10 to the 8th. So where's that 10 to the 5th come from? And that, I know to write the speed of light. I've written the speed of light here in kilometers per second because Hubble's constant is given in kilometers per second. So 3 times 10 to the 8th meters per second is equal to 3 times 10 to the 5th kilometers per second. And that is where that comes from. When I put that into my calculator, I get that my distance is 370 megaparsecs. Now let's take a moment to look at the mark scheme. So as you can see, this is a 2-mark question. I can tell that because there's 2 lines on the mark scheme. So the first mark came from using z to find v. The second comes from correctly substituting that value for v into your equation for Hubble's law. So I want to talk about one other way that we can understand and use z, and that is by looking at the cosmic scale factor, which is the ratio between the current size of the universe and the size of the universe at whatever point in time I'm interested in. So I can actually use my redshift to figure out how big the universe was when something that I measured the redshift for generated the light that I am seeing. So let's take a look at another example. A spectral line in the hydrogen spectrum in a laboratory today has a wavelength of 21 centimeters. Since the emission of the cosmic microwave background radiation, the cosmic scale factor has changed by a factor of 1100. Determine the wavelength of the 21 centimeter spectrum in the CMB radiation when it is observed today. So I'm going to go ahead and start by just labeling my variables. So lambda naught, that's going to be the wavelength when that light was emitted. And we know that the scale factor has changed by a factor of 1100. So that's going to give me R naught over R. And from here, it should be pretty easy to solve this question. So I know that Z is equal to r naught over r minus 1, and it's also equal to delta lambda over lambda naught. So that means that delta lambda, which is what I'm interested in, is equal to lambda naught times r naught over r minus 1. Or delta lambda is equal to 21 centimeters times 1100 minus 1. That gives me a shift in lambda of 23079 centimeters. And that is going to be equal to delta lambda, which is lambda now minus lambda naught. Now, lambda naught is 21, so what that gives me is that lambda is equal to 23079 centimeters plus 21 centimeters, or 23090 centimeters. I would likely round this to just 23,100 centimeters, or 231 meters. Is show you all the mark scheme, and again, we can see the answer given here is 23,100 centimeters. So taking a quick look at the mark scheme, you can see this is a 1-mark question. So you get your marks for either writing 23,100 or 231. You'll notice the units here are in brackets. So what this means is that either answer would be accepted even if you did not specify your units. So let's go ahead and talk takeaways. First, the universe is expanding, which is causing distant objects to be redshifted. Second, we can predict the age of the universe using the magnitude of that redshift. And third, we can determine the rate of expansion of the universe by looking at the redshift from distant galaxies. So there you have it. This is your introduction to Hubble's law.